Hi everyone, I welcome you all to the video lecture on about the procedure to draw the V and inverter vehicles of a synchronous motor by conducting experiment in the AC machines laboratory. So the objective of this experiment is, as the name itself says, so we are going to draw the V and the inverter vehicles of a synchronous motor, and thereby we are going to understand the performance of the synchronous motor and how the performance, that is the V and inverter vehicles, can be applied to the suitable application of the synchronous motor as a synchronous condenser. So this is a synchronous motor, we see that. So as the name mentions, that is a synchronous motor. The synchronous motor should always run at a synchronous speed. The synchronous motor has two major parts, the stator and the rotor. The stator is fed by a three-phase supply which induces a rotating magnetic field. So initially, based on the structure of these damper windings available over the field coils, this rotor starts rotating as a induction motor. So after some time, when you start giving the DC supply, the field and the rotating magnetic field gets synchronized, and the rotor also starts running at the synchronous speed by creating a magnetic lock between the stator magnetic poles and the rotor magnetic poles. This is the typical characteristics of a synchronous motor. So is a model graph, you see that. So it is drawn between IF and the armature current or the line current of the synchronous motor. So if you look at this graph, you see that so when the excitation current of the synchronous motor or the field current of this synchronous motor, that is this part of the circuit, this part of the machine is changed, you can find that when the field current moves from zero current to the maximum possible, the IL initially starts reducing, and after some times it starts increasing. So this takes the shape of a U or a V curve. So we call it as the V curve here. And similarly, if you draw the graph between IF and the power factor, so you are getting an inverted V curve. So you see that when IF is less, the power factor is also less, but it is lagging. So when you keep on increasing the excitation current, so the power factor gradually increases in steps. It gradually increases in steps and this reaches the maximum value as unity power factor. If you further increase the excitation current, you can find that the power factor starts reducing, but in the leading portion. So this is one of the very special characteristic of the synchronous motor, because it operates at three different power factor ranges as lagging, leading, and also in unity power factor ranges. So this is what we are going to get it by conducting experiment, and then by drawing the graph we are going to get the characteristics of the given synchronous motor. And this is a circuit diagram. So in this circuit diagram you see that there are three parts of this circuit. So what are the three parts? You can see that, so this part you call it as the synchronous motor. Of course this is synchronous motor stator part, and this represents the field part of the field control or field part of the synchronous motor, and this is a kind of loading arrangements, so that you are going to give it to the synchronous motor. So these are the three different things which we are going to apply for conducting our experiments. So initially, so what we are going to do is close the TP-STS. I am going to close this TP-STS, so that by which the three-phase supply is given to the machine. So using this starter, the synchronous motor is started. The synchronous motor is now started. So what next I have to do here is, you have to increase the excitation current in steps, by changing by changing the rheostat resistances available in the excitation circuit of the synchronous motor. Each and every time when you change the excitation current, you have to measure the field current, the line voltage and the armature voltage, or otherwise the line current of the synchronous motor. So these are the things you have to measure for each and every step or each and every variation in the excitation current. So this is one experiment what we have to do now. So after taking these readings, so these readings are said to be called as the no-load reading, as this part of the circuit is not going to be considered now. So now what we are going to do is, so you are going to adjust this resistance in such a way that rated voltage can start building up in this motor, which is in this generator motor, which is now acting as a generator. So once the rated voltage is generated, so you have to close this DPSTS. That means the load is connected to the generator now. So once the load is connected, keep adding the load. By keeping the load as constant. Again change the excitation current in this circuit from lower level to higher level step by step. Again measure the IL, VL and the WL with respect to this IF. So this experiment you have to repeat for 1 or 2 load values. So totally for no load value, and at load condition you can take at 1 or 2 values. By keeping the load fixed, you have to repeat the experiments here. So the load may be 1/4 of the rated load, 1/2 of the rated load, or it can be full load conditions. So taking the readings for different load conditions will help you to have a detailed analysis of the characteristics of the machine. So after completing this, we have to go to the calculation thing, which is, so in this the only calculation that you have to do is using the power IL and VL. You have to find out the power factor. So after getting the power factor, draw a graph between IF and IL, that gives the V curves, and draw a graph between IF and the power factor you get using W, VL and IL. So that gives the inverter power factor. Draw it for the different load values you have taken now. So once the calculations are over, draw the V and inverter V curves in the given graph sheet. So try to find out the reason behind the change in line current with the change in excitation current, and also the change in power factor with respect to the change in the excitation current of the synchronous motor. Also analyze how the load that is given to the synchronous motor has an influence over the V and inverter V curves. So what is the shift in the V and inverter V curves you obtain with respect to the addition of the load? So these are some of the things you have to interpret, and you have to record it in your observation as well as in your lab report. Thank you.